Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back to Physics with Beth and Beth. I'm Beth and today we are doing our final video on the final unit of the core AP Physics 1 curriculum. We are doing some higher level applications of Bernoulli's principle, the grossest, longest, and final equation on your AP Physics 1 equation sheet. In our last video, my fellow Beth walked you guys through what exactly that equation means and the ideas behind it. It's really just the conservation of energy applied to fluids. So if you guys still feel a little shaky on that, or if you haven't seen that video, I would really recommend watching it. She does a great job. But in this video, we're going to work on an application of that very equation. And to do that, we're going to go through this gross pile of word salad that I have on the board here. So the best place to begin is the beginning, so let's dive right in. Here's the problem that we have. We have water flowing through a circular pipe with a constant radius of 10 centimeters. At point A, which is labeled in this little diagram here, the speed of the water is 5 meters per second and the pressure is 300,000 pascals. And we're asked to find the speed of the water at point B, right here, and also the pressure at point B. So this is our little drawing here. And okay, let's first talk about this part A here. What is the speed of the water at point B? Well, first, one of the really important things that we're going to need to note to solve this problem is that we have a constant radius. The radius of our pipe isn't changing. Our pipe is the same size throughout. And a way that we can relate the size of the pipe to its velocity is this helpful little continuity equation here, the second to last equation on your AP Physics 1 equation sheet. So what the continuity equation tells us, if we apply it here, is that the cross-sectional area of our pipe at point A times the velocity of our fluid at point A has to be equal to the cross-sectional area of our pipe at point B times the velocity of my fluid at point B. Now, here's the thing though, we were told that our circular pipe has a constant radius, right? So if I took a little cookie cutter slice of my pipe at any point along its path, that little cookie cutter slice is going to be exactly the same size. My cross-sectional area is constant throughout this whole pipe. So the cross-sectional area at point A is the same as the cross-sectional area at point B. So I'm just going to rewrite this as the cross-sectional area at point A times the velocity of my fluid at point A times the cross-sectional area at point A, because, well, these two things are the same, so I can just replace them one for the other, times the velocity at point B. Well, now I have the cross-sectional area of point A on both sides of my equal sign. I'm just going to divide both sides by that and cancel it out. And now we're given that the velocity of our fluid at point A is equal to the velocity of our fluid at point B. But wait, that feels a little wrong, doesn't it? Like, there's a part of our brain that almost wants to say, well, this is like a roller coaster problem, right? If I have a roller coaster going along a track and then it goes up a hill to be at a higher level, my velocity has to decrease. This is conservation of energy. My kinetic energy is being turned into potential. I have 1/2 mv squared plus mgh is equal to 1/2 mv squared plus mgh. If my potential energy goes up, my kinetic energy has to go down, right? But there's something wrong with that idea. Well, it's not that that's wrong. That's still true. Conservation of energy always applies, and it even applies here. It's what we're using. But there's one extra piece that you're missing in that little explanation. I would give you a challenge to pause the video here and try and think of what that missing piece might be. All right, now what that missing piece is that we don't only have potential energy and kinetic energy at play here. We also have work being done on our fluid. There is a force that is pushing our water through this pipe that is putting energy into our system. So yeah, we are increasing our potential energy here, which is going to cause us to lose energy from somewhere else. But where we see that being applied here isn't in a lowering of our velocity. It's going to be affecting that work piece of the equation. And we'll get more into that in the second part of this problem. But think about it like this. If my water was slowing down as it went through this pipe, well, say I have a chunk of water here, and it goes up through my pipe and it slows down in this top section. If I had more water coming in and it was going at this faster speed, well, this water hasn't moved on yet. It's going slower. There wouldn't be anywhere for the new water to go. So if my water slowed down as it went through the pipe, then I would get this backlog. My water wouldn't be able to move anywhere, and soon I would have no motion at all. So if you have a constant flow through a pipe, which is what you're going to be dealing with whenever we have dynamics in fluids here, then you're going to need to not slow down your water if your pipe stays at the constant radius. If my pipe got bigger, okay, well now then we can talk, which my fellow Beth does do in our previous video. But for now, let's move on to part 2 of this here. Well, first of all, just to clarify for part 1, what is the speed of our water at point B? It's the same as it is at point A, so therefore it's still 5 meters per second. I should have written that out, and I should label it with units, or else you will lose points on the AP Physics 1 exam. Remember to label it explicitly with units, it's important. All right, but now let's move on to part B. What is the pressure at part B? Well, now we get to use that big, ugly, gross equation that my fellow Beth taught us about. This one right here, Bernoulli's principle that says that the pressure at point 1 plus the density times the acceleration of gravity times the height at point 1 plus 1/2 the density of my fluid times the velocity of my fluid at point 1 squared is equal to all of those same values at point 2. So here, instead of points 1 and 2, we have points A and B. I'm going to erase all of my gross words up here so I have a bit of room to write. Here we go. I really should have written that down before I do. Let's write this down real quick. Our pressure at point A is 300,000 pascals. Yeah. There we go. Our pressure at point A is 300,000 pascals. Our velocity is 5 meters per second, and our radius is 10 centimeters. I'll just drop that down in case we need to use it. Okay, so what is the pressure at point B? Well, the pressure at point A plus rho, or the density of my fluid at point A, times the acceleration of gravity times my height at point A, I'll do a capital A here to be consistent in my notation, plus 1/2 the density times the velocity of my fluid at point A squared has to be equal to the pressure at point B plus rho, the density of my fluid, times the acceleration of gravity times my height of point B plus 1/2 my density times the velocity at point B squared. That's really gross, but we can simplify this down a little bit. First of all, we know we're looking for the pressure at point B. Well, that's this term right here. This is the guy that we're looking for. Thankfully, we also know our speed of our water stays exactly the same. Our velocity at point A is the same as our velocity at point B. So I'm just going to subtract this term from both sides because it's the same. Our density of water is always 1,000 kilograms per meter cubed. Our velocity isn't changing, it's still 5 meters per second. So this term here is exactly the same as this term here. So if I subtract it from both sides, they end up canceling out and leaving us with 0. So now we just have 4 terms, which is so much less gross, thank goodness. The pressure at point A plus the density times the acceleration of gravity times the height at point A is equal to the pressure at point B plus the density times the acceleration of gravity times the height at point B. Goodness gracious, I run out of breath just saying that. That's a lot of letters. Okay, but we know that the height of our pipe at point A here is this little y1 value. It's 0 meters. And then our height goes up to y2 to being 8 meters. A quick reminder that whenever we plug in the height of our pipe, you use the center line of the pipe, not the bottom or the top, the center line, because you're talking about the average height of all of the fluid in your pipe. So you go through the middle of your pipe whenever you set that. So YA will be our Y1, Y2 will be our YB. Our height at point B is 8 meters. So I'm going to erase a little more here so I have a little more room. Our pressure at point A. And actually, I'm going to rearrange this a little bit to solve for the pressure at point B, because that's what we're looking for, right? I don't want to start plugging in numbers until I absolutely have to, because as gross as all of these letters are, the numbers are going to be even grosser. So I'm going to rearrange this to solve for the pressure at point B by subtracting this term from both sides to bring it over here. So I have the pressure at point A plus my density times my acceleration of gravity times my height at A minus my density times the acceleration of gravity times my height at B is equal to my pressure at point B. Now I'm going to do a little bit of algebra here and just combine these terms because I want to do as little math as possible. I am always a big fan of working smarter, not harder. So I'm going to erase this here so I have more room. I'm going to combine these guys. So I have my pressure at point A. I'm going to combine these by factoring out my density times the acceleration of gravity. So my density times the acceleration of gravity times YA minus YB. So that's just a little bit of algebra there, is equal to my pressure at B. And now that I have this all written down, I know my pressure at A, I know the density of water, it's pretty much unchanging, it's just 1,000 kilograms per meter cubed. I know my height at point A, it's 0. I know my height at point B, it's 8. And this is what I'm solving for. So all we have now are letters that represent numbers we know, and on the other side, the thing we're looking for. So we are good to go now. So all I'm going to do is plug in those values here. So I have 300,000 plus 1,000 times 9.8 times 0 minus 8, which is negative 8, is equal to PB. And when you plug this all into your calculator, you end up solving, you end up getting that this is 300,000 minus 78,480 is equal to my pressure at point B. And then when we solve for it, we end up finding that my pressure at point B is equal to 221,520 pascals. All right, so we have our answer, but before we put away our papers and pencils, let's talk about this for a second. Our pressure of our fluid at point B is 221,520 pascals. That's lower than our pressure was at point A, lower than the pressure that we started out with. And if you're anything like me, that almost feels a little counterintuitive. We're going the same speed and pressure feels like something that's related to speed, so shouldn't our pressure stay the same too? But think of it like this. Fluids always flow from areas of high pressure to areas of low pressure. That's what drives changes in weather, air pressure. Wind moves from places of high pressure to low pressure. That's what drives changes in fluids too. Things go from high pressure to low pressure because they get pushed in that direction, right? If my pressure was higher here, my water would never get through the pipe and we would never be able to drink the glass of water from our fridge. And that would be really sad. Everything would be bad and gross. Thankfully though, our pressure is lower here. And the reason why all comes from Bernoulli's principle. Our velocity was the same because of the continuity equation, because our cross-sectional area stayed the same. So our water had to be going through the same speed through every spot in our pipe since there was just as much space for the water to go. But Bernoulli's principle tells us that as our height increases here, our pressure decreases. A way that you can think of it might be the pressure is sort of like the outside energy that's coming in and pushing our water forward. As we're going to a higher height, well, now our water has more potential energy. That energy had to come from somewhere, and the place that it comes from is the pressure. So higher height, lower pressure if your cross-sectional area stays the same. All right, guys, thank you so much for sticking with me through all of that. I know Bernoulli's principle is a doozy, but you all have been troopers and have done a great job sticking with me throughout this whole video and through this whole semester. I wish you guys the best of luck on your upcoming AP Physics 1 exam. If you guys have any questions, please feel free to let us know in the comments and we will do everything we can to respond and answer those questions for you. And if these videos have been helping you all out at all, please let us know. We read every single comment and they really make our day. Miss Beth texts me every single time one of you guys leaves one. But thank you so much, guys. Good luck on your upcoming exams. We'll be there right there with you in spirit, if not physically in the room. And happy physicsing.